one of the biggest challenges that we are facing is that of climate change. And as part of that, the energy transition is crucial. Interestingly, lots of people are discussing this in the media and politics. Strangely enough, it's almost never about uncertainty. And what I will try and convince you of today, that uncertainty is crucial in making these decisions and should be incorporated, especially in the long-term view. So what is the energy transition? Well, that's the transition from non-sustainable to sustainable energy sources. And we know what those are. Those are solar and wind, biomass, and also other sources are available. For instance, marine sources, like wave energy. I won't be discussing that today. Basically, I'll be focusing later on in the Netherlands on solar and wind, which is mainly what we have available, and not so much on biomass. We actually have quite a bit of biomass at the moment, relatively, but there's lots of discussion about it, how green it is actually, and also it's got limited potential if you look at the whole of the Netherlands. One thing maybe to note here as well is I've put down the non-sustainable sources, and of course that includes nuclear, which has come up in the discussions a lot lately. That is clearly not a sustainable source. So the main challenge then is to, of course, we have the supply and we have the demand to match them. It's a key challenge in supply chain management in general and running operations. Why is that difficult for sustainable sources? Well, because they're unreliable. Right? Sometimes we have lots of wind, sometimes we don't. Sometimes the sun is shining, sometimes it doesn't. So how do we actually match the unreliable sources with the also unreliable demand? That is one of the key challenges. Already we can see that because both sides are unreliable and we don't always produce when we need the demand, we will also need storage. Now, one of the options to do that is hydrogen storage, and I won't focus on the details today, but basically I'll be focusing on that and the costs of that. So indeed, let's focus for today only on the Netherlands. And we'll also limit our systems to solar and wind energy. Again, like I said, biomass is an option, but also a limited option. We'll include a storage option as well. Now note that actually from now on, storage I'll refer to as inventory. That may seem a bit strange, but as is for solar also later on in the model, so to avoid confusion, what I'll do is I'll talk about inventory rather than storage. And again, the key question is how much wind, how much solar, and how much storage do we need to actually ensure that we can always satisfy the demand? Well, we can't always ensure that, but with a high probability we want to be sure that supply is more than demand. And then we go to basically explaining why we need operational research, also sometimes called operations research in other countries. Well, because we're dealing with uncertainty, and deciding under uncertainty is really hard and requires decision science operational research tools. Now what do we always do? We take these steps. So we collect the data. In this case, I won't show you how I collected the data, but the main data you can imagine is first of all from the Central Bureau of Statistics, that's in the Netherlands, who collect lots of data about energy demand and so on. And the second part is of course weather data. It's about wind and solar, and in the Netherlands the KNMI is the main source for that weather data. So we collected that weather data. Second step, we build a model, and I'll actually build that model with you. Then we find a solution. I will basically show you the solution, and then also I will interpret it with you. Because it's not about the solution in itself, it's about what we can actually learn from the solution. So let's go to the first bit of data, and this is energy demand. Now you could make lots of scenarios. First of all, it's quite clear, and everybody knows this, we're actually using more and more energy all the time, which is basically a bad thing, right? Because it also means you need to supply more energy. Now some people think it goes down a lot, may go down a lot in the future. Others think it's stable. For my model, it doesn't matter that much, but from a scenario I'm going to take, basically I'm going to look at a basically stable supply around like 3,300. Because if you look at the last, say, decade, that's about where it is. Then let's have a look at the demand data. And obviously, the demand changes over the year, right? In the winter it's colder, so actually, especially in the Netherlands, we use a lot more gas to heat our homes. So we use more energy in the winter than we do in the summer, so we have a monthly pattern. That also means that when I make estimations, I need to do it at the monthly level. Maybe actually you could do it at the daily, the weekly level, make the model more detailed. I won't do that for today. For today, I'm going to take the monthly level. Now also what you see is various lines. In this case, I've limited to 4 lines so you can see them clearly. What is obvious that, of course, the demand and also the demand per month differs per year. So if you take 4 years, you've got 4 data points. Now that's good, that's actually excellent. We need multiple years. Why? Well, we need only not to have the average or a point in 1 year. And interestingly, that's what lots of people have done in the past, to look at one scenario. No, we need to look at uncertainty. And to grasp uncertainty, you need to have multiple data points and look at things like a standard deviation. So what we've actually done here is we estimate the mean per month and the variance, or the standard deviation, and now we fit a distribution around that. In this case, we stick to normal distributions, and I won't go into the details of that. Then we've got radiation, so basically solar energy. Again, we see a pattern, and already we see the biggest downside, which is well known of solar panels, which is they produce lots of energy in the summer, but you need it in the winter. Right, it's not that black and white, but that's a problem. On the before slide you saw, we need lots of energy in the winter, and we have lots of sun in the summer. Luckily, wind energy is better. There's a bit more wind in the winter than there is in the summer. However, you can also see the biggest downside of wind already. There's a lot of variation over the years. So wind speed varies a lot, also comparable to solar radiation. So that's an advantage of solar over wind. There's another advantage of solar over wind, and that is that if you look at solar panels, of course they won't take up all the radiation, but they take about, say, 18%. Studies differ, but for today I'm going to assume about 80%. So 80% of the radiation you take in is there. With wind it's different. The relation between the wind speed, which we already saw varies a lot, and wind energy is quite complex. First of all, that's what we call a cut-in speed, below which the rotor won't turn, right? If there's not enough wind, it's not turning. There's also a cut-out speed at the end, at about 25 meters per second, but there's so much wind, it's risky to actually have it turn. In between is still very variable. In between, when wind speed increases by a factor of 2, wind energy increases by a factor of 8. Now that is good, but it also works the other way around. You halve the wind speed, you have only 1/8 of the wind energy, which is not good. So there's a lot of uncertainty about wind energy. That's one of its downsides. So what's better, basically, right? Wind or solar? Now, what I'm going to do is also have some other data here. Now, we've looked at sources, and basically, based on those sources for today, and I'm going to say, solar energy is about 7 cents per kilowatt hour, and wind is slightly more cost efficient at 6 cents. And then we need storage, like I said. And again, based on assumptions, here we just assume for today, there's a cost for that which is 19 cents per kilowatt hour. It's also important to remember that actually storage isn't easy. I talked about hydrogen. What does that mean? Well, we've got solar, we've got windmills. They produce energy, electricity. We have to turn that into storage, into hydrogen. And then there's a 20% loss. So we lose 20% of the energy, right? So also the other way around, we lose 20% again. So then later on, when we take hydrogen, make electricity out of it, we again lose 20%. So all in all, you retain 80 times 80, 64% only of what you generate. So about 2/3. Now, let's build a model, right? So let's use operational research. We start with there has to be an objective. And obviously, let's today say it's cost. We have wind capacity that we're building, and there's a cost for that, like I said. It's like 6 cents per kilowatt hour. Solar is a bit more expensive, there's 7, and we need inventory capacity, right? So I take the C for capacity in this case. I do that because later on in my model I have an I for the actual inventory as well. Well, that's okay. But what are the conditions then? Well, first of all, the storage is there, and I need to progress the inventory that I have. How do I do that? Well, think about it. Suppose I have something in my inventory in January. Then what do I have in February? Well, I have what I had in January, minus what I took out of the storage, plus what I actually put in to the storage. Well, that's exactly what it says here. And you have that for every month, not just for January, but from February to March, etc. So we have all these conditions. Now I also know, I said in my model, that all these inventories, they always need to be less than the capacity that I'm actually building and paying for. So that's the second condition. Then you can imagine that what goes in must come out. You cannot take out of storage long run what you don't put in. So we have this condition over the year. Now, I told you up front, we're also going to have a buffer energy. Why? Well, I don't only want to look at the case where we're having 100% clean energy, because that will take time. So I'm going to look at the transition over time from having only 10% clean energy to 100% clean energy. The rest of the energy is produced by a buffer source that I will not model. I will just say it's able to do 10 or 20 or 30% of the total amount of energy. Now note, one important assumption I'm making is that if you're using 30% of this buffer energy, you don't need to use 30% every month. You can use more in the winter than the summer. So it's a flexible source, and that's important because, like I said, solar is there in the summer, so you want your other source to be there in the winter, basically. So it's a flexible source. So only the total has to be below my capacity. And now comes the crucial bit, the difficult bit, where you really need your operational research, and that's here. So what do we want? Well, we want supply and demand, and supply needs to be more than demand, almost surely. So on the right, actually, already you see there's a 1 minus epsilon, and I will assume this epsilon to actually be small, like 1%, and that means there's a 99% probability I've got enough. So when do I have enough? Well, you have enough when the total production, plus what you take out of storage, is more than demand. So how much do you have? Well, you've got your wind production, and it's typically offshore, so actually I made it blue to show it's basically from the sea, and then you've got your on-land solar production normally, that's your S. Well, times what they bring, right, which is the difficult bit, because that's the uncertain bit. And what we actually do is we draw those from the distributions we estimated. Then we also take stuff from the buffer, and we may take things from the storage finally, times 80%, right? Because then we lose 20%, and as long as that's more than demand, we're happy. Because supply is more than demand, and everybody has the electricity that they want. Okay, and finally, you have to tell programs and computers that all the decision variables are positive. This may seem obvious, but actually the computer wouldn't know, so you have to tell it actually, for instance, that you cannot build negative amount of solar panels. That's the complete model, right? We have tools for solving that, and I won't, of course, go into that today, but basically the tools we're using are tools of stochastic optimization. So we optimize under uncertainty, and stochastics is just another name for uncertainty. Right, so let's go to the results, which are quite surprising and fascinating. So at the bottom, what I do is I look at 10 to 100% clean, sustainable energy. So on the left, 10%, it means 90% is still from the buffer. Think about oil and coal and so on. On the right-hand side, everything is sustainable. So what do we see? Early on during the transition, there's lots of green. Lots of solar is optimal. So it might seem like a good idea for now to actually build lots of solar panels. And in a way, the government is doing that. They're financing that. But what we also see is long-term, that is not a good idea at all. Because long-term, if you move to the right, the panels disappear. And more windmills come about. Why is that? Well, actually, what happens to the right is that the buffer goes down, right? You're becoming more sustainable. What is nice about the buffer, it's flexible. So the buffer covers the fact that although the solar panels don't produce a lot in the summer, in the winter early on, the buffer can do that. But as the buffer disappears, you need sources that actually produce when you need it to avoid the storage. So when you move to the right, actually, you see, you have a lot more wind than you have solar. One thing to note on the right as well, note is that when you look at the height of the bar, is close to 5,000. But remember, maybe not the first slide, it showed us that the demand was only above 3,000. So why is that? Well, that is because of the uncertainty in the demand, but also in the supply. So actually, I'm showing you this to just show the importance of uncertainty. If I would ignore the uncertainty on the left, I would produce exactly what I need, my 3,300 by wind and solar. On the right, you see, that won't do. Because if you do that, you hit the average, basically half of the years, half of the months, you won't have enough. So it won't work. So you need the extra capacity. And only through a careful stochastic optimization will you find out exactly how much capacity you need. Then a nice thing about building a model is you can also do a robustness, a sensitivity analysis, and we've done that here. In my model, you may remember that I said actually that wind is slightly less costly than solar. And you may think, okay, that explains the results, but it doesn't. Because here what I do is, okay, I said, in the base case, I said 7 cents for solar, but what if I change it? What if I make it 6 or 5 cents? So 5 cents would actually be less than wind energy. Well, even at 5 cents, you see basically there's no change. Even if solar is more cost efficient than wind, you're still basically using more wind, lots more wind. If, of course, solar becomes really cheap, then at some point you will change to more solar, and you see that here. But the results are quite robust. So what have we learned? 2 things. First of all, let's talk about energy. What we've learned about energy is that considering uncertainties is crucial. Right? So I'm just saying to all the politicians, media and so on, from now on, talk about uncertainty as well. The reason they don't is lots of people find it difficult actually to deal with uncertainty. The second is, and I think that's also really crucial, from a long-term perspective, we have to be careful with solar capacity. And actually the energy world is saying this as well. They're seeing to be built lots of solar panels everywhere, and maybe actually that is not a good idea long term. Thirdly, certainly during the transition and even afterwards, what we need ideally is a flexible extra source. Maybe biomass, but it's limited, but maybe some other source that we can burn when we need it. And certainly not a nuclear facility, because basically that produces at the same level the whole year. But that's not what we need. We've got these unreliable sources that we can't actually put on enough, so we need another source that we can put on enough. So even if nuclear, and it's come up rather lately in the discussions, even if it were to be cost efficient, which most experts say certainly it isn't, even then it would not be a sensible option at all. Finally, just a note on why maybe you should study more operational research, because basically it allows you to do these sorts of analysis, and that will also contribute not only to decision problems in the economics and in businesses, but really also attack the main societal problems. I talked about energy here, but a healthy future with all the uncertainties with it is just another example. Thank you for your attention.